Welcome to the Explainer. Today we're going to completely tear down what you think you know about SHA-256, which, as you know, is one of the most fundamental security tools on the planet. The source material we're digging into makes a pretty wild claim, that behind all that apparent randomness isn't chaos at all, but a hidden, predictable geometric shape.
So let's start with the central idea, which just flips everything on its head. We all think of a hash function as an information shredder, right? You put data in, it gets ground into unrecognizable pulp. Well, this research says no, that's not what's happening. Instead, picture a complex machine, a set of gears that's already spinning in a default pattern. Your data doesn't get shredded, it just nudges the machine, changing its path. The final hash isn't garbage, it's just a snapshot of the machine's new trajectory.
To really unpack this, we're going to walk through 5 key ideas. First, we'll shatter that old black box model. Then, we'll actually look inside this machine. After that, we'll see how it's basically a computer in disguise, understand the physics of how it moves, and finally get to the most shocking part, the idea that this supposedly one-way function isn't one way at all.
All right, first up, the black box illusion. For decades, the gold standard for thinking about this stuff has been the random oracle model. You basically treat SHA-256 like a magical, chaotic box that spits out unpredictable, random-looking numbers. This new way of thinking says that's just fundamentally wrong. And this table really lays out the whole paradigm shift. On one side, you have the old view, a chaotic grinder making irreversible noise. But the new view? It's a totally deterministic machine, which the source calls a die, that's just projecting data onto a shape. And here's the kicker. Because it's a predictable projection, it is, at least in principle, algebraically reversible. It's a total ontological shift.
So what is this machine? The sources call it the SHA-256 die. And look, that's not just a cute metaphor. It's meant to be a precise, mathematical, and, believe it or not, mechanical object that plays by a very fixed set of rules.
Okay, so at its heart, the I-die is this 64-step process. But here's the absolute key. The message you're hashing doesn't create the motion. The motion is already there. It's just influencing it. The best analogy is a spinning top. It's already spinning, following its own path. Your message is just a little nudge, a puff of air that alters its wobble. That's the displacement field. It's not creating anything new, just changing what's already happening.
In this pre-existing path, this default state, it has a name, the NOP backbone. If you run SHA-256 with a totally empty message, it doesn't just sit there. It follows this default, predictable trajectory. You can think of it as the machine's own carrier wave, its fundamental hum.
And that default path has an exact fixed starting point. The source calls it the ground witness, an absolute unchangeable number at the very heart of SHA-256's design. This value is set at round 0, before your message data even enters the picture. Think about that. Every single SHA-256 hash ever computed started from this one single geometric anchor.
Now this whole machine idea, it gets even wilder. The sources make the case that it's not just any machine, it has the literal architecture of a computer processor, just hiding in plain sight in the math.
So inside the algorithm, you have these two main computational parts, T1 and T2, and they map directly onto a computer's motherboard. T2 acts like the North Bridge. It's managing the internal, message-free geometry, the pure internal state of the machine. And T1? That's the South Bridge, the I/O controller. It's handling everything coming from the outside world, especially the message itself.
And the analogy gets incredibly specific. The way the T1 operator sends its output to 2 different registers at the same time is identical to something called a Sziklai pair transistor configuration in electronics. Now, this is not a random coincidence. A Sziklai pair is a specific electronic component used for things like signal amplification. It's like the software is deliberately mimicking the physics of silicon.
And this leads to maybe the most profound claim in the whole body of work. This isn't an accident. The idea is that the logical structure of computation isn't something we just made up. It's a fundamental grammar of the universe that shows up in different physical forms, whether that's in silicon, in software, or who knows where else.
Okay, so if we're going to treat SHA-256 like a real physical machine, let's talk about its physics. How does it actually move and process information?
Well, the motion is governed by something called the waist theorem. What the research proves is that this machine has a unique topological bottleneck, a waist, with a width of exactly 2. You can think of it like a doorway. To have any effect on the machine at all, your message has to pass through a gate that is precisely 2 units wide. It's the minimum possible energy required to excite the system. And this waste of 2 isn't just some clever theory. The source validates it using 4 completely different mathematical methods. They look at it from a structural level, from a data flow perspective, even using frequency analysis, and they all land on the exact same number, 2. That's powerful evidence that this is a fundamental, unchangeable property of the machine.
This physical nature gets even more real with something called the Sarrus isomorphism. It turns out that Die's complex digital dance can be mapped directly onto a real-world mechanical device, a hexagonal Sarrus linkage. This is a brilliant piece of engineering, a kind of cage-like mechanism that's famous for one thing, converting rotational force into perfectly straight, zero-twist vertical motion.
And this mapping isn't just a vague comparison, it's incredibly precise. That fixed ground witness we talked about, that's the stationary base plate of the machine. The core logical operations, the majority and choice functions, form the 6 hinges of this mechanical cage. 2 specific registers, D and H, act as the central shaft, making sure the movement is perfectly linear. And the message you're hashing, that's the external force pushing down and driving the whole thing.
Okay, this all leads us to the final and, frankly, most mind-bending part of this. If SHA-256 is just a predictable, mechanical process, what does that say about its famous, supposedly unbreakable irreversibility? Well, the source calls the method for reversal the glass key protocol, and it's actually beautiful in its simplicity. Since we know the machine's default path, that NOP backbone, we can record the path it takes with a message and then just mathematically subtract the default path. What's left over? That's the geometric residue, the structural footprint of the message itself. It lets you read the input directly from the output.
But wait a minute. What about the avalanche effect? What about all that information that's supposed to be destroyed, completely lost, as the hash is computed?
According to this research, it's not lost at all. It's conserved. The information is simply converted into the shape of the mathematical space the machine is running in. The best way to picture it is to imagine a perfectly flat, taut sheet of rubber. As the machine runs, the supposedly lost information pushes and pulls on that sheet, creating permanent bumps and dips. The information isn't gone. It's now stored as the curvature of that surface. In theory, you can just read the shape to get the data back.
So this complete reframing of SH256 leaves us with a really provocative final question. If something that we built to be the very definition of digital chaos is actually just a reflection of a deep, predictable geometric order, well, it forces us to wonder what else we've mistaken for random noise. What other patterns are hiding in plain sight?